Hi everyone! Today we're going to talk about this roller coaster that's built by Jessica, Cathy, Tina, and Marie. So we have basically three parts in this roller coaster. The first part is this big hill. This is landmark A, and then we have a loop here, and this is landmark B, and finally we have this small hill down here, and that's landmark C.
This roller coaster is very different from our original designs. We had to make a few changes. The first change we had to make is this huge hill right here. You can see that the stick is really pulled back because at first we designed it to be straight up, which makes it a really tall hill, but then that won't work because the ball will just jump right off because it's a 90-degree angle. So instead we change it to this huge hill. And then we also make this loop smaller because originally we had the loop to go from here to here, which is a huge loop, but then the momentum from the big hill is not enough to support it through the big hill and then that. So instead we change it to a smaller loop. And also finally we changed the small hill. At first it was supposed to go up after the turn, but then it's not enough momentum, so instead we make it to go down.
For landmark A, we have the highest point to here, which is our initial height is 0.7 meters, and then as the ball goes down, it lands to its final height is about 0.175 meters. Landmark B, we have the highest point, which is around here to here. The initial height is 0.3 meters, and its final height, which is right behind, it's about 0.15 meters. We also measure the radius of this loop. It's about 0.0825 meters. Landmark C is initial height is 0.175, final height is 0.05 meters.
Potential energy equals to mgh, which is mass times the gravitational acceleration times height. So first we measure the potential energy at the highest point, which is the velocity is 0.0084 kilograms times 9.8 times the height,
0.24 meters,
and we get the result of
0.02 joules.
And the second point is the loop, which is mgh, which is the mass times 9.8 times 0.31, get a result of 0.026. And lastly, we calculate the potential energy at a small slope, which is right here, and the height is 0.065 meters. And finally, we get the potential energy of 0.005 joules. Next, we calculate speed, which is distance divided by time. We use photo gauge to measure the time that the ball required to pass through the 0.035 distance that is between the two sensors of the photo gauge, which is at landmark A, B, and C. And then we take 4 trials of each landmarks, and eventually we average the 4 trials to get our average speed. For landmark A, we eventually get 2.1146 meters per second, and then at landmark B, we get an average of
1.402
meters per second, and at our final landmark C, we got like a 1.25246 meters per second. Now we calculate the kinetic energy, which is equal to 1/2 mv squared, and we use the velocity that we just calculated from the previous calculation, and then we have the mass of 0.0084 kilograms, and eventually at landmark A we get the kinetic energy of 0.019 joules, and then at landmark B we get 0.06 joules, and at landmark C we get 0.07 joules.
The first free body diagram is landmark A.
Here's the free body diagram. There are 3 forces acting upon the roller coaster. The first force is force normal, which is perpendicular to the surface that is being acted upon. And the second force is for friction, which is the opposite direction to the that is moving towards. And the third force is force mg, which is gravity times its mass.
At landmark B, there are a total of 3 forces acting on the small ball. So the first one is the friction force, which is in the opposite of the motion the ball is traveling to, so it's pointing this way. And there's the gravitational force and the normal force, which is both pointing downwards. Due to the circular motion, the small ball is also experiencing a centripetal acceleration.
Here we have landmark C.
Force gravity is perpendicular to the Earth's surface, and force friction is the opposite direction the body is moving towards. And then here we have force normal, which is perpendicular to the contact surface.
And now we calculate the friction between point A and point B, which is the energy loss. And we use the final potential energy plus the final kinetic energy minus the initial potential energy and then minus the initial kinetic energy. And finally we get negative 0.007 joules.
Now we're going to calculate the friction between point B and point C, and it's the same, pretty much the same as the previous calculation. Finally, we got the answer of negative 0.02 joules.
Now we calculate the centripetal acceleration. So acceleration is velocity squared over radius. From the previous calculations, we know the radius is 0.0825 meters and velocity is 1.1943 meters per second. So the final calculation is 17.29 meters per second squared.
First, we calculate the force for landmark A. The equation for force is force equals ma, and then the equation for acceleration is velocity over time. So we calculate the force, which we get the result of 1.07 newtons.
Next we calculate the force at landmark B. And we use the same equation and we get a result of 0.337 Newton. Finally, we calculate the force at landmark C. We repeat the equation and we get the result of 0.3764 Newtons. Our sources of error, which includes air resistance, unexpected movements of the ball and roller coaster, as well as human errors that occur during measurements.
In conclusion, through the roller coaster project, we have learned more about Newton's law, circular motion, energy, and work. But most importantly, we learned about collaboration as we all contributed equally to the project.